Hello there, and welcome to Sleepy Traveler, where every distant light becomes a quiet story to fall into. I'm glad you've drifted into this little corner of the night with me. Outside, the universe is carrying on in its own soft way, stars burning steadily, galaxies turning like slow lanterns in the dark. Tonight, we'll follow a slightly different path through that darkness, not to the familiar suns and gentle planets, but to the oddities hiding in the shadows, stars that feed their companions, tiny engines that outshine whole galaxies, collapsed hearts of matter that bend space itself, and dead stars that still spin and sing with impossible strength. We'll visit these strange objects the way you might walk through a gallery after hours, soft steps, low voices, plenty of time to linger. If this kind of gentle wandering through the cosmos brings you comfort or curiosity, a quiet like and a soft subscribe help others find their way here too. For now, we'll just begin, together, in the dark. Out there, the universe is not just a scatter of ordinary stars. It is threaded with places that don't quite fit our simple pictures of how a star should look or behave. Some strange objects are born from rare accidents, the kind that need many different conditions to line up just right. Others are strange simply because they push some property, brightness, density, gravity far beyond what feels reasonable. A few hide so well that only careful instruments can find them. Others are bold enough to shine straight into the naked eye. Imagine, for a moment, that you're gliding quietly through this cosmic sea, and someone is gently pointing out the oddities. Over there, a lonely star trailing a ghostly ribbon of gas behind it, like a comet drawn out to impossible lengths. Farther on, a knot of light where thousands of suns have been pulled into a region so tight that the whole cluster would fit comfortably inside the space between our sun and its nearest stellar neighbor. Deeper in, you pass objects that don't shine like normal stars at all, collapsed hearts of matter that send out pulses, flashes, and invisible storms of energy, punching their rhythm into the dark. Along this path, you meet tiny but fierce beacons called pulsars, spinning so fast that they sweep their radiation across space like lighthouse beams. You brush past black holes, those regions where gravity has clenched so tightly that even light cannot slip free, yet the space around them blazes with energy as matter falls inward. Somewhere nearby, a magnetar turns in the dark, its magnetic field so strong it could tear at the structure of atoms from a distance that feels almost safe. And if you drift your thoughts far into the future, you might find black dwarfs, quiet, cooled remnants of once brilliant stars, their long drama of burning finally ended. But before you wander that far, your attention catches on a single, peculiar point of light. There is a star ahead whose story is already unfolding into space around it, written not in words, but in a long, pale trail. This is where the journey pauses first, at a star called Mira. Most stars in our Milky Way behave in a way that feels almost modest. They slowly circle the center of the galaxy, moving along with the surrounding gas, not racing too far ahead, not dragging too far behind. Their speeds are different, but not dramatically so. Our own sun, for instance, drifts through the thin mist of the local interstellar cloud at about 25 kilometers each second. That sounds fast in human terms, but among stars it's a calm, steady pace. Mira is not calm. Compared to its neighbors, it is a sprinter. It cuts through the interstellar gas at around 130 kilometers per second, more than 5 times the sun's speed relative to its local cloud. At that pace, Every second, it travels farther than the distance between some of the largest cities on Earth. Over 1 minute, it covers more ground than a jet would in hours. Over a human lifetime, it crosses space in a way that feels almost reckless for something so large and so old. When an object that massive moves that quickly through the thin gas between the stars, it cannot help but leave a mark. Mira has been shedding material for a long time, peeling off layers of gas from its outer regions as it nears the end of its life as an ordinary star. Because it is racing ahead, the material it releases does not simply gather around it like a gentle mist. Instead, the wind of its motion pushes that material backward, stretching it out into a long, faint tail that streams behind it through the interstellar medium. If you could step outside the galaxy and look down with the right kind of eyes, you would see Mira followed by a luminous trail several light years long. That tail is what makes this star one of the most unusual and captivating sights in the constellation Cetus, the Whale. It's as if Mira has been drawing a line through space for tens of thousands of years, leaving behind a record of where it has been. For a long time, no one knew this tail existed. Astronomers had been watching Mira for over 400 years, carefully tracking its changing brightness. They knew it was interesting. They knew it varied, sometimes shining clearly, sometimes shrinking back until it was barely noticeable. But through the lenses and photographic plates used in visible light, the sky around it looked mostly blank. That changed in 2007 when a space telescope called Galaxies, an observatory that studies the sky in ultraviolet light, turned its gaze toward Mira. Ultraviolet light is higher in energy than what our eyes can see. It reveals processes and structures that are invisible in ordinary photographs. When astronomers processed the Galaxy images, the familiar point of light that marked the star was there, but now it had a long, distinct tail stretching out behind it. What had once been an ordinary-looking star in visible light suddenly revealed itself as a comet-like traveler in ultraviolet. The tail, made of gas and dust that Mira had shed, extended about 13 light-years into space. That distance is roughly 3 times the gap between our Sun and its nearest stellar neighbor, Proxima Centauri. In terms of human experience, it is almost impossible to imagine. Yet on the scale of the galaxy, it is a single, graceful stroke. The discovery was puzzling at first. How could something so large, so extended, have stayed hidden for so long? The answer lay not in the tail itself, but in the kind of light it was emitting. The particles in the tail, mostly hydrogen atoms, were gradually losing the energy they had carried away from the star. As they calmed, they released that energy as ultraviolet radiation. Our eyes are blind to that glow. Only a telescope designed to see in the ultraviolet could reveal it. The tail had always been there, quietly following Mira through space. We just didn't have the right kind of vision to notice. Mira is not simply pouring out a little gas now and then. Every decade, it sheds an amount of material roughly equal to the mass of the Earth. If you imagine our planet, with all its mountains, oceans, and core, being translated into a fine gas and dust and blown away into the dark every 10 years, you get a sense of how much matter is leaving the star. By combining the length of the tail and the star's speed, astronomers can work backward and estimate how long this process has been going on. The material at the very far end of the tail appears to have been ejected about 30,000 years ago. Over that span of time, the total mass Mira has shed into its trail may be comparable to about 3,000 Earths. That is a staggering number, and yet It fits naturally into the life story of a star nearing its final peaceful transformations. It has grown large and diffuse, and its outer layers are only loosely bound. Bit by bit, those layers drift away, and the star leaves some of itself behind in the spaces it travels through. The tail is not the only structure Mira has carved into the interstellar medium. Ahead of the star, in the direction of its motion, there is another feature that Galax helped reveal, a kind of glowing arc, like a bow wave in front of a ship. As Mira moves through the gas between the stars, the material at its front collides with the thin interstellar particles, compressing and heating them. Over many years, these interactions build up a curved, wave-like front ahead of the star, a bow shock that marks the boundary where Mira's outflow and the interstellar gas meet. If you picture a boat cutting through calm water, you can see a V-shaped wave forming at its bow, the water piling up in front and then streaming away to the sides. Mira is doing something similar, but with stellar wind and interstellar gas instead of water. The star, its tail, and its bow shocked together create the impression of a luminous vessel cleaving through a very thin cosmic ocean. Only here, the water is so sparse that you could travel for kilometers without meeting a single atom, and yet, over vast distances and long stretches of time, even such thin material can be shaped and lit. Most of what Mira sheds is made of hydrogen, the simplest and most common element in the universe. As these hydrogen atoms leave the star, they are energized by the conditions in Mira's outer layers and by their collisions in the tail and bow shock region. Over time, they lose this extra energy and emit ultraviolet light, which is what Galax detected. We see the tail not directly as a stream of gas, but as a ribbon of cooling atoms, quietly letting go of their stored energy. The star at the heart of all this is itself an object full of character. Mira is known as a pulsating variable star. Its brightness does not stay constant. Instead, it swells and fades in a repeating cycle, as if it is slowly breathing in light. At its brightest, Mira becomes the most luminous star in its constellation, easily visible to the naked eye from dark skies. At its faintest, it shrinks to a point that is difficult to see without binoculars, dimmer by a factor of many thousands compared to its peak. On average, its apparent brightness is around magnitude 3.5, but depending on the phase of its pulsation cycle, it can vary between about magnitude 2 and magnitude 10. For comparison, Sirius, the brightest star in our night sky, shines at about magnitude 1.46, much brighter than Mira ever becomes. The way Mira's light waxes and wanes has been watched and recorded for centuries, making it a kind of old friend to generations of skywatchers. Mira is also not alone. It belongs to a binary system, meaning it has a stellar companion. The main star, the one with the long tail, is called Mira A. It is a red giant, a star that has swelled up late in its life and become cool and large. Its partner, Mira B, is a white dwarf, a small, dense leftover core of a star that has already passed through its own giant phase. Together, they sit about 417 light-years away from Earth. The distance between them is on the order of 70 astronomical units, roughly 70 times the distance between the Earth and the Sunday. That separation is wider than the orbit of Neptune, yet in cosmic terms, the two stars are still close companions. Mira A's mass is estimated to be about 1.2 times that of our Sunday. If you could weigh the two, Mira A would come out only a little heavier, but its size tells a very different story. Its radius is about 360 times that of the Sunday. If you placed Mira A where our Sun is, its swollen outer layers would extend out beyond the orbit of Mars and deep into the region of the asteroid belt, perhaps brushing against where the Earth now orbits. A star with a mass not so different from the Sun has become a sphere enormous enough to swallow much of our inner solar system. The reason it can be so big without being overwhelmingly massive is that its average density is extremely low. Mira A, like other red giants, is puffed up and diffuse. Its outer layers are so spread out that its mean density can be thousands of times less than that of water. If you could somehow scoop out a star-sized bubble of its outer atmosphere and place it in a giant cosmic tank, it would float easily. The Sun, by comparison, has an average density slightly higher than that of water. In becoming a red giant, Mira A has traded compactness for volume. Its internal structure has rearranged, its core has contracted, and its outer layers have expanded and thinned. Despite its cool surface temperature of around 3,000 Kelvin cooler than the Sun's roughly 5,800 Kelvin photosphere, Mira A shines with a luminosity about 9,000 times greater than that of the Sunday. This is the effect of its huge surface area. Each square meter of its surface emits less energy than a square meter on the Sun, but there are so many more square meters that, added together, the total output is enormous. From a distance, it glows as a powerful red beacon. Mira is thought to be about 6 billion years old, older than our Sun, which is currently around 4.6 billion years into its own life. Time has already worked many changes on this star. It spent a long era as a more ordinary object, a yellow dwarf not too different from what our Sun is today. That phase is behind it now. The core has used much of its hydrogen fuel. Layers of fusion and shell burning have reshaped it. It has expanded, cooled at the surface, and begun to let go of its outer layers. Because Mira A is not massive enough, its story will not end in the violent fireworks of a supernova. Instead, its finish will be quieter and more graceful. As it continues to evolve, it will shed more and more of its outer envelope, adding fresh material to the tail and the surrounding space. Eventually, those expelled layers will form a glowing shell around the hot core, a planetary nebula, a delicate bubble of gas lit from within. For a while, this nebula will stand out as a soft, colorful cloud. Then, over time, it will disperse into the surrounding interstellar medium, mixing with the wider galaxy as the star's remaining heart settles down into the compact, enduring form of a white dwarf, and the gases it once held close continue their slow drift through space around it. While the future white dwarf core of Mira A is quietly taking shape beneath its thinning layers, there is already a white dwarf close by, keeping it company. This second star in the system, Mira B, reached that compact, dense stage long ago. It is small by stellar standards, a burnt-out heart that no longer shines by fusing fresh fuel, yet it has not faded into silence. Its story is tied to the outflow from its swollen red giant partner. By the loose measure of the galaxy, Mira B sits very close to Mira A. Because they are so near, the gas drifting away from Mira A's outer layers does not always escape into open space. Some of it falls under the pull of Mira B's gravity instead, spiraling around the white dwarf as it loses energy and settles. In this way, a hot accretion disk has formed around Mira B, a flattened ring of infalling matter, slowly feeding the small, dense star at its center. The gas that once belonged to the red giant now moves along curved paths around the white dwarf, heating up as it rubs and collides with itself. As this material gradually falls inward onto the white dwarf's surface, it releases bursts of energy. The light from Mira B is not steady. It flickers and changes with the rhythm of the material arriving. Because of this, Mira B is also a variable star. Its apparent brightness, as seen from Earth, shifts between about magnitude 9.5 and 12. Sometimes it can be picked out with a modest telescope under dark skies. At other times, it slips toward the threshold of invisibility. Both members of this system, then, are variables: Mira A, with its deep, slow pulsations, and Mira B, with the restless feeding of its accretion disk. Elsewhere in the universe, there are many other stars whose light waxes and wanes over time. Some vary because they eclipse one another in binary systems. Some change as spots, flares, or magnetic fields alter how their surfaces radiate. Others, like Mira A, truly swell and shrink in size as their outer layers respond to the forces within. All of them fall under the umbrella of variable stars, objects whose luminosity is linked to physical processes either inside them or very close by. Studying these variables is one of the keys to understanding how stars grow old and change. A star that is changing in brightness is often standing at some kind of crossroads, adjusting to a new balance of forces, burning a different kind of fuel, shedding mass, or interacting more strongly with a companion. Variable stars are, in many cases, stars caught in the act of becoming something else. Mira has become so important in this way that its name has been given to an entire class of objects. The peculiar features of this star, its large size, its cool surface, its strong pulsations, its dramatic changes in brightness made it a natural prototype. Stars that behave in a similar fashion are now called Mira-type stars, or Mira variables. The name is a quiet acknowledgement that this single wanderer in Cetus helped reveal a broader family. Mira variables are pulsating giant stars of late spectral type. That simply means they are old, expanded stars with relatively cool surfaces, glowing more red than white or blue. They spend this late chapter of their lives in slow, rhythmic instability. Their brightness, as measured from Earth, typically ranges from about magnitude 2.5 at their brightest to around 11 at their faintest. When they are near their peaks, some of them can be seen with the naked eye under good conditions. Near their lows, the same stars may require binoculars or a telescope, or may fade completely from unaided sight. These giants are in the process of shedding their outer envelopes. Over spans of a few million years, a short time by stellar standards, they lose a substantial fraction of their mass to space, letting it drift outward as a wind. Eventually, like Mira A is expected to do, they will peel away so much of their outer layers that only the dense core remains. That core will contract into a white dwarf, while the ejected gas forms a nebula that slowly thins and disperses. Most Mira-type variables are not especially heavy in terms of total mass. They are thought to be no more than about 2 times the mass of the Sunday. Yet, in their bloated, red giant phase, they can shine thousands of times brighter than the Sunday. Their outer layers have expanded enormously, so they present a vast radiating surface. Even though each patch of that surface is relatively cool, the overall glow is tremendous. The pulsation of these stars is a compromise between gravity pulling inward and the pressure of hot gas and radiation pushing outward. As conditions inside the star change, its outer layers can fall out of balance. In one part of the cycle, the envelope contracts and heats. As it is compressed, the temperature rises, the pressure increases, and the star pushes outward again. In the next part of the cycle, those outer layers expand, cool, and thin, allowing gravity once more to gain the upper hand. This back and forth motion changes both the radius and the surface temperature, which in turn makes the luminosity rise and fall. In principle, planets could still orbit such stars, though their lives would not be simple. The changing brightness, the strong stellar winds, and the eventual loss of large amounts of mass would reshape any planetary system over time. Around most Mira variables, we do not yet have clear evidence of planets. Only one star of this type, R Leonis, in the constellation Leo, is currently suspected to host a planetary system, and even there, the existence of planets remains unconfirmed. If you pull your view back from a single Mira variable, even from a whole binary system like Mira A and Mira B, another pattern begins to emerge. Stars rarely appear entirely alone. Many are born in groups, sharing their first light with hundreds or thousands of siblings. These groups are called star clusters, a gathering of stars that formed out of the same enormous cloud of interstellar gas and dust. Because they come from one parent cloud, the stars in a cluster tend to share similar ages and chemical compositions. Their motions are tied together too, held in a loose but real embrace by gravity. Star clusters are often divided into two main families: open clusters and globular clusters. Open clusters are the children of stellar nurseries regions where large clouds of gas, rich in hydrogen, have collapsed and fragmented. Inside these clouds, new stars are actively being born. Because they have only recently formed, the stars in open clusters are mostly young and often quite hot and bright. The gravity binding the members of an open cluster together is comparatively weak. Over the course of several 100 million years, an open cluster gradually loosens. Stars at the edges can be disturbed by the wider gravitational field of the galaxy or by encounters with other clouds and clusters. Little by little, members escape. The cluster spreads out and eventually dissolves, its former stars becoming part of the general stellar background of the Milky Way. Even after a cluster has dispersed, some of its former members can still move together through space, sharing a similar velocity and direction. These lingering associations are called stellar streams, quiet remnants of once more compact groups. Other stars born in the same cluster become wanderers, traveling on paths that no longer hint at their shared origin. In our galaxy, more than 1,100 open clusters have been cataloged so far. Many clusters are hidden by dust, faint with age, or simply too distant to be easily recognized. Globular clusters are a different experience altogether. Where open clusters are modest and temporary, globular clusters are massive and enduring. They are larger, denser, and far older than their open cousins. A globular cluster can contain hundreds of thousands to 1,000,000 stars, all swarming in a roughly spherical ball bound by strong mutual gravity. The stars here are typically old and relatively low in mass. Inside a globular cluster, the average distance between neighboring stars is small by galactic standards, on the order of 4 to 6 light months. The total mass of such a cluster may reach 1,000,000 times the mass of the Sunday suspended in the halos of galaxies. These ancient systems are like fossilized cities of stars. The Milky Way contains at least about 50 known globular clusters. Our neighboring Andromeda galaxy appears to have more than 500. Between the open clusters and the grand globulars, there is another category that draws attention: so-called superstar clusters. These are open clusters that are unusually rich and massive, hosting thousands of stars within a relatively small volume. In size, they are modest. In population, they are crowded. Some astronomers suspect that the largest of these superstar clusters may be the seeds of future globular clusters. Given enough time, a few billion years, their most massive stars will burn through their fuel quickly and end their lives in supernova explosions. The cluster will lose some mass but may settle into a more tightly bound, long-lived configuration. One of the largest superstar clusters known in our own galaxy is called Westerlund 1. It was first identified in 1961 by the Swedish astronomer Bengt Westerlund. For many years after its discovery, Westerlund 1 remained poorly understood. Dust and gas in the plane of the Milky Way dim and red in its light, and its own internal crowding makes it hard to disentangle individual stars. Careful measurements place Westerlund 1 at a distance of roughly 10,000 to 15,000 light-years from the Sunday. The number is huge in human terms, yet for a cluster of this type, it is relatively close, making Westerlund 1 one of our nearest superstar clusters. The physical size of Westerlund 1 is surprisingly compact. Its diameter is about 7 light-years. Within that sphere, which is tiny compared to the full breadth of the Milky Way, thousands of stars are packed together. The total mass of the cluster is estimated to be around 63,000 times the mass of the Sunday. Simple calculations show that the typical distance between the major stars in the cluster is only a few light months. Binary systems, pairs of stars orbiting each other, can be much closer still. Because the stars are so densely packed and still partly wrapped in the clouds of interstellar gas from which they formed, their light blends and overlaps. Through a telescope, the cluster's core can resemble a single, intense glow, rather than a neat sprinkling of separate points. This makes it difficult to identify and count the stars one by one, and to attribute the light precisely to each source. Even so, through careful observation and patient analysis, astronomers can tease out structure within this crowded little city of suns, using Westerlund 1 as a quiet but powerful window into the lives of stars born in close company. When you look into Westerlund 1 with patient eyes and careful instruments, it becomes clear that counting its stars is not a simple task. The cluster is so dense, so veiled in gas and dust, that individual lights blend into one another. The exact number of stars remains uncertain, still waiting to be teased out from the glow. Even so, astronomers have been able to identify several remarkable types among the crowd. There are yellow hypergiants, 6 of them, immense, unstable stars, swollen to enormous sizes, shining with a brightness that pushes at the limits of what their own gravity can hold together. There are 4 red supergiants, even cooler and larger, their outer layers drifting and simmering, hinting at futures filled with powerful explosions. Scattered among them are at least 24 Wolf-Rayet stars, stripped down, fierce objects that have already lost much of their outer shells, and now roar with powerful stellar winds. Somewhere in the mix is a supergiant with an unusually strange emission spectrum, likely the product of a collision or close interaction between 2 massive stars in the not-so-distant past. Beyond these headline figures, Westerlund 1 also hosts many hot blue giants. young massive stars burning their fuel quickly and intensely. Among this population, an X-ray pulsar was discovered, a neutron star spinning with astonishing speed, sending out pulses of high-energy radiation as its magnetic field and rotation channel particles into narrow beams. In the steady hum of the cluster, this pulsar is like a tiny, relentless metronome ticking away in X-rays. The number of binary stars in Westerland 1 is also unusually high. Many of its stars are paired, bound to one another by gravity and circling a common center of mass. In such a crowded environment, this is hardly surprising. Close encounters between stars are much more likely here than in calmer regions of the galaxy. When massive young stars form near one another, it is easy for gravity to link them in orbit. Some pairs may even have formed through interactions after birth, as passing stars snared one another into long-term partnership. All the stars in this cluster are thought to have formed at roughly the same time in a single episode of star formation. They are like siblings, born from the same collapse of a giant molecular cloud. Yet, even if they share a birthday in cosmic terms, they do not share the same fates. The more massive a star is, the faster it races through its stages of life. Stellar evolution theory tells us that red supergiants, the kind we see here, cannot be younger than about 4 million years, given how quickly massive stars evolve into these swollen forms. Wolf-Rayet stars, which are even more advanced in their life cycles, are by definition near their ends. Their total lifetimes almost never exceed about 5 million years. The fact that Westerland 1 contains so many Wolf-Rayet stars and red supergiants at once is a powerful clue. It suggests that the cluster's age is tightly constrained, around 4 to 5 million years. In the story of the universe, that span is almost nothing, a few heartbeats. On Earth, around the time these stars were forming, the world was already home to early hominins and large mammals like saber-toothed cats. The dinosaurs had long since vanished, leaving only fossil traces in stone. While our planet was reshaping its ecosystems after ancient extinctions, this dense pocket of space was just beginning to blaze with newborn giants. When astronomers model how a cluster like Westerland 1 forms and evolves, they find that in order to produce the mix of stars seen today, the cluster must originally have contained between about 50 and 150 extremely massive stars. These would have been the true titans, the first to ignite, the quickest to race through their fuel, the earliest to die. With lifetimes of only a few million years, many of them should already have reached their final acts, exploding as supernovae and leaving behind compact remnants, black holes, neutron stars, or, in some lighter cases, white dwarfs. If those estimates are right, Westerland 1 would have experienced a supernova roughly every 10,000 years over the last million years or so. That is an astonishing rate when you think of such explosions as rare, dramatic events. In Westerland 1, they would have been part of the background story, occasional, violent endings punctuating a sky already bright with stellar light. The more massive the star, the faster it moves through its life. These heaviest stars burn hot and bright, exhaust their nuclear fuel quickly, and then collapse. Depending on the mass of what remains after the explosion, they may leave behind a neutron star, a compact, city-sized sphere packed with neutrons, or a black hole where gravity is so intense that even light cannot escape, Given how many massive stars Westerlund 1 likely had in its youth, you might expect to see black holes and neutron stars scattered throughout. Yet, so far, only one compact remnant in the cluster has been unambiguously identified: the X-ray pulsar, and a magnetar we will come to in a moment. Many black holes may indeed be there, but they are quiet, difficult to detect unless they pull matter from a companion or interact strongly with their surroundings. They hide in the glow of the cluster, their presence inferred more than seen. Among the visible swollen stars of Westerlund, one is a particularly extraordinary object, one of the largest stars known. It is usually referred to as Westerlund 126. This star is hard to study in detail because of the same problems that affect the rest of the cluster: distance, dust, and crowding. But astronomers have been able to estimate its size. Its radius is somewhere between about 1,500 and 2,500 times that of the Sunday. If the true value lies near the upper end, Westerlund 126 would challenge for the title of the largest known star. Current understanding, however, suggests that the real size is likely closer to the lower estimate, just over 1,500 solar radii. Even that is almost beyond imagination. If you placed Westerlund 126 where our Sun is, its outer layers would swell past the orbits of Mercury, Venus, Earth, and Mars, flowing outward until they brushed or even surpassed the orbit of Jupiter. The inner solar system, as we know it, would lie deep within its extended atmosphere, despite having a relatively cool surface temperature of around 3,000 Kelvin, more like a glowing ember than a searing white-hot flame. Westerlund 126 shines with a luminosity roughly 380,000 times that of the Sunday. The sheer size of its surface more than compensates for its lower temperature. Its exact mass is harder to pin down, but from what we know about how stars of this type form and evolve, it is probably around 20 times the mass of the Sunday. A great deal of weight has been expanded into a vast, tenuous sphere on the edge of stability. Another standout member of Westerlund 1 is a magnetar, an object with a name that feels like a little tongue twister. A highly magnetized neutron star and one of the most powerful sources of X-ray radiation in that region of space. It lies about 16,000 light-years from the Sunday. Like other neutron stars, it is the collapsed core of a massive star that ended its life in a supernova. Packed into a sphere only a few tens of kilometers across, it contains more mass than the Sunday. On top of that, its magnetic field is staggeringly strong. This magnetar rotates once every 10 seconds or so. For a neutron star, this is actually slow. Many pulsars spin several times per second, and some whirl hundreds of times per second. The magnetar's measured period, combined with the knowledge that all the stars in Westerlund 1 are of a similar young age, lets astronomers work backward. The star that gave birth to this magnetar must have had a total lifetime of only about 5 million years before it blew apart. That means its original mass must have been at least 40 times the mass of the Sunday. The puzzle is that stars with initial masses that high are generally expected to form black holes, not leave behind neutron stars. If the progenitor of the magnetar truly started with 40 solar masses, something dramatic must have happened to strip away most of that mass before the final collapse. Calculations suggest that it would have had to lose around 95% of its mass before the supernova. One possible explanation is that the magnetar's ancestor was not a solitary star, but part of a close binary system. Two massive stars orbiting each other rapidly can exchange large amounts of material over time. As they spin around their common center of mass, tidal forces and stellar winds peel matter from one and feed it to the other. Eventually, one star reaches the end of its life and explodes. The supernova can blow away the remaining outer layers and hurl the companion outward, breaking the pair apart. The compact remnant here, the magnetar, is left behind amid the wreckage. Within Westerland 1, there is a star known as Westerland 1-5, relatively near the magnetar's position. Some astronomers suspect that this star may once have been the magnetar's companion, flung away when the supernova occurred. The idea is compelling, but the evidence is not yet conclusive. Like many things in astrophysics, it remains a quiet, open question. Given all this drama, massive stars, supergiants, magnetars, past supernovae, it is natural to wonder whether planets could exist in such a place. The answer, as far as we can tell, is that the odds are not good. For one thing, the stars in Westerland 1 are very young. Planet formation is a slow process, taking hundreds of millions of years, at minimum, for solid worlds to grow, cool, and settle into stable orbits. Westerland 1, at only 4 to 5 million years old, has barely had time to let its stars fully mature, let alone to assemble complex planetary systems. Even if you look far ahead, imagining Westerland 1 aging and relaxing into a globular-like cluster over billions of years, it still seems an unlikely haven for life as we know it. The close proximity of large, heavy stars in such a dense environment makes planetary orbits fragile. Gravitational nudges from passing stars can distort or even eject planets from their systems. In some cases, a massive neighbor might pass close enough to tear apart a protoplanetary disk or disrupt an existing planetary family altogether. On top of gravitational instability, there is the radiation environment. Thousands of active, luminous stars squeezed into a relatively small region of space create a strong background of high-energy photons and particles. Supernova explosions, which are more frequent in such clusters when they are young and massive, can flood nearby space with intense bursts of gamma rays and other harmful radiation. Any fragile biosphere on the surface of a planet would face repeated challenges, its atmosphere battered, its chemistry reset. Even in a distant future where humans or their descendants learn to cross interstellar distances, clusters like Westerland 1 may remain places to approach with caution, extraordinary laboratories for studying how stars live and die, but harsh neighborhoods for life. They are beautiful to look at from afar, but not gentle. As you drift away from Westerland 1, inch your thoughts, carrying with you the image of a small, crowded city of suns filled with giants, pulsars, and magnetars. Your attention can settle on another class of strange systems that echo some of the same themes on a different scale. Scattered throughout the galaxy are objects called microquasars. These are usually X-ray binaries, stellar pairs, in which one member is a more ordinary star, not so different from our Sun, while the other is a compact object, a black hole, or a neutron star. In these systems, matter from the normal star is drawn toward the compact companion, forming an accretion disk as it spirals inward. As that matter falls, it heats to tremendous temperatures and shines brightly in X-rays. At the same time, some of the material is not swallowed immediately. Instead, it is redirected and launched outward along narrow jets at very high speeds. sometimes approaching a significant fraction of the speed of light. In these systems, the outflows of matter that escape, instead of falling inward, are called jets. They are narrow, focused streams of plasma, launched along the axis of the compact object's rotation, threading outward into space like two thin beams. In miniature, the behavior of these jets mirrors what happens on a much grander scale in the cores of distant galaxies. That is why astronomers name these systems microquasars. They are small echoes of quasars, sharing similar physics in a much more compact setting. The resemblance is not perfect, of course. In a true quasar, the central engine is a supermassive black hole buried in the heart of a galaxy, weighing millions or even hundreds of millions of times as much as the Sunday. Around it, an enormous accretion disk blazes, and jets can stretch for thousands or even millions of light years, punching far beyond the galaxy itself. In a microquasar, the compact object is modest by comparison, just a few times the sun's mass, or a few tens at most. The jets it produces are shorter, its reach more local, its voice quieter on the cosmic stage. But in some ways, this smallness is a gift because the masses involved are smaller, the timescales are shorter. Where the giant machinery of a quasar may take years or centuries to noticeably change its jets, a microquasar can flare and vary far more quickly. In these smaller systems, jets may be born, strengthen, weaken, and shift almost daily. The same basic script is being performed: matter spiraling in magnetic fields, twisting it, some of it launched outward instead of swallowed, but the tempo is faster, easier to follow. The key differences between microquasars and regular quasars lie in their masses and the cadence of their activity. In a microquasar, the compact object might have a mass of just a few suns to perhaps a few dozen solar masses. By contrast, the black hole in the center of a quasar often tips the scales at around 100 million solar masses or more. One is a dense ember from a single star's death. The other is a colossus built over long ages from the merging and feeding of many stars and gas clouds. Despite their smaller size, the accretion disks of microquasars are anything but quiet. As matter spirals inward, it heats to tremendous temperatures and glows intensely, especially in X-rays and optical light. On a human scale, these systems are bright, violent places. The compact object is wrapped in a brilliant, whirling disk, with jets cutting away from its poles. To understand why astronomers chose the name quasar in the first place, it helps to picture one of these larger cousins. A quasar, short for quasi-stellar radio source, from the days when they were first identified, is one of the most luminous kinds of object in the observable universe. According to current understanding, a quasar is the active core of a galaxy whose central black hole is feeding vigorously. Gas and dust falling towards the black hole flatten into a huge accretion disk. As this material rubs together and falls inward, it releases staggering amounts of energy. The glow from a quasar's disk can be hundreds of times brighter than the combined light of all the stars in a galaxy like the Milky Way. The jets launched from the vicinity of the black hole carry energy and particles far into intergalactic space. Even from billions of light years away, some quasars appear bright enough to be detected with relatively small telescopes. A few can even be glimpsed without optical aids from exceptionally dark locations, tiny points whose light has been traveling toward us since the universe was younger. So far, astronomers have cataloged more than 200,000 quasars. Microquasars, in contrast, are rare in our lists. The catalog of known microquasars contains only a small number of entries. Some of this difference may simply be because microquasars are harder to recognize. They hide among the many X-ray binaries in our own galaxy and in nearby ones. But part of it also reflects reality. The specific conditions needed to produce strong relativistic jets on a small scale are not met in every binary. The first object to be identified as a microquasar was discovered in 1978. Two astronomers from the University of Cambridge were studying unusual radio and X-ray emissions while looking for remnants of past supernova explosions in the constellation Aquila, the Eagle. Among the sources they examined was one that did not quite fit the expected patterns. It showed strong, persistent outflows and a complex spectrum. This object later received the designation SS-433. SS-433 is an eclipsing X-ray binary system, meaning that from our point of view, the two components periodically pass in front of one another, causing dips in brightness. One member of this pair is believed to be a black hole, the compact primary. The other is a more ordinary star of spectral type A, a hot main sequence dwarf of whitish hue. This companion's mass is thought to be between roughly 10 and 30 times that of the Sunday. In its earlier life, it may have been even more massive, losing material over time through winds and transfer to its partner. The surface temperature of this star is estimated to lie between about 7,000 and 11,000 Kelvin. That is typical for A-type stars and gives them a pale, bluish-white or slightly yellowish tint. If you think of some of the bright stars near the Sun, such as Sirius or Altair or Vega, you are thinking of the same general class. In SS-433, however, this familiar kind of star is locked into a very unfamiliar situation. The entire system sits inside a larger structure, the supernova remnant, known as W50. On some images, this remnant has a shape that reminds observers of a sea creature, earning it the nickname the Manatee Nebula. The age of W50 is estimated at around 20,000 years, and its distance from Earth is about 18,000 light years. The jets from SS-433 push against and distort the gas and dust of the surrounding remnant, carving long, faint lobes into it. One widely held idea is that W50 and SS-433 share a common origin. The supernova that created W50 may also have given birth to the compact object in SS-433. In that picture, the explosion about 20,000 years ago left behind a black hole or neutron star, which then began interacting with its companion star, forming the binary we see today. The remnant nebula is the expanding shell of the original blast, while SS-433 is the enduring, active heart at its center. The two components of SS-433 orbit their common center of mass with a period of about 13.1 days. That means that in less than 2 weeks, each completes a full circuit, locked in an endless dance. Because the orbit is oriented in such a way that one star can pass in front of the other from our line of sight, their brightness changes in a regular pattern as they eclipse one another. The flow of matter between them is what makes the system so striking. Gas from the ordinary star spills over toward the compact primary, pulled across by gravity. As it falls, it does not plunge straight in. Instead, it gathers into a rotating accretion disk. In that disk, friction and compression heat the gas to extreme temperatures, causing it to emit X-rays and other high-energy radiation. Part of the infalling material is channeled along magnetic field lines and launched outward instead of being swallowed, forming the two jets that give SS-433 its micro-quasar status. These jets stream away from the system at about 26% of the speed of light, roughly 79,000 kilometers every second. At that speed, a particle could circle the Earth in less than a second. The jets are composed of hot, ionized gas and extend far into the surrounding nebula, pushing and shaping the material they encounter. In 2019, using the ALMA Observatory in Chile, astronomers obtained detailed images of SS-433 at millimeter wavelengths. These observations allowed them to map the structure of the jets with new clarity. They found that the jets themselves are relatively narrow, but their shapes are not simple straight lines. Instead, they have knots and irregularities, places where the emission brightens or twists. Further studies showed that the unusual shape of the jets is strongly influenced by precession, a slow, conical wobble of the jet axis over time. As the compact object and its accretion disk rotate, the direction in which the jets are fired gradually changes, tracing out a spiral. The effect is similar to watching a spinning top as it slows down. The axis of the top does not stay pointing in one direction, but sweeps out a circle. In SS-433, the precession of the jets means they carve out corkscrew-like paths through space. The diameter of each jet's influence, as it expands outward, may reach distances thousands of times larger than the size of the solar system. Imagining that scale is difficult. Picture our sun and the orbits of its planets as a tiny circle, and then imagine a coil wrapped around it that is thousands of times larger, formed by streams of gas moving at a significant fraction of light speed. Because SS-433 is relatively close to Earth compared to many other energetic systems, it has become a particularly valuable laboratory for studying jet physics. The ALMA images did more than just show the jets clearly. They also confirmed theoretical predictions about their shape and motion. In 2018, before these detailed images were taken, astronomers using the Global Jet Watch telescopes had made spectroscopic measurements of SS-433, analyzing how its light was shifted by motion. From these data, they constructed models of how the jets should look if precession was occurring in a certain way. When the ALMA data arrived, the actual jets matched these predictions closely. SS-433 truly appeared to have the corkscrew structure that had been drawn from earlier spectral clues. It was a quiet but satisfying alignment between theory and observation, a reminder that even in such wild environments, the universe still follows rules we can learn to read. Jets, like those from SS-433, are not unique to this system. Across the universe, similar streams of plasma relativistic jets are seen emerging from the centers of active galaxies, from quasars, and from radio galaxies. In those cases, the jets can be far larger and more powerful, but their basic nature is the same: matter heated and accelerated in the grip of strong gravity and magnetic fields, flung outward along narrow paths. Typically, there are two jets pointing in opposite directions from the central engine, like two beams from a cosmic lighthouse. This is exactly what we observe in SS-433, a compact, binary system, wrapped in an accretion disk, launching twin jets out into the surrounding nebula, a small yet vivid version of a process that plays out on scales, from a few light hours to across entire galaxies. The sight of jets like those from SS-433 leaves a quiet question hanging in the mind. How, exactly, does a system manage to launch matter so cleanly and so fast into space, instead of simply swallowing it all? The deeper astronomers look, the more it seems that these jets are woven from the interplay between magnetic fields and the hot, swirling accretion disk around a compact object, a black hole or a neutron star. As gas spirals inward, its motion and the rotation of the compact object twist magnetic field lines into tight, coiled structures. Those fields can grab some of the infalling matter and fling it outward along the rotation axis, focusing it into narrow streams. The result is a pair of jets that pierce the surrounding space, like two threads drawn straight through a moving, luminous fog. The size of such jets can be astonishing. In some radio galaxies, they extend for many thousands of light years, far beyond the bright central region that launched them. In the case of the radio galaxy known as 3C120, for example, the jet stretches for at least several kiloparsecs, tens of thousands of light years from its source. A structure born near a black hole smaller than our solar system manages to influence regions of space larger than whole galaxies like our own. Back in the more intimate setting of SS-433, the story of the ordinary star and its compact partner is still unfolding. Over time, it is likely that the regular star in the system will lose more and more of its outer layers, stripped away by the gravitational pull and radiation of the compact object. Its core, still hot and dense, will remain behind as the envelope drifts away. When that happens, the star will become what astronomers call a hot subdwarf, a kind of exposed stellar core, small and very hot, shining with a hard, intense light. Even that stage may not last forever. Given enough time, the compact object, likely a black hole, can continue to draw matter from the subdwarf, steadily feeding from what remains. Gradually, the subdwarf will be whittled down, its mass siphoned off and added to the black hole. Sooner or later, the SS-433 system may settle into a simpler configuration, a lone compact object, its earlier companion reduced to little or nothing, the history of their interaction written only in the nebula around them and in the spin and mass of the survivor. Black holes like this are, by their nature, difficult to detect. They do not emit light of their own that can reach us. Any radiation we see comes from the matter around them, from the accretion disks, the jets, the heated gas they disturb. A black hole that is not actively feeding is nearly invisible, marking its presence only through subtle gravitational effects on nearby stars or gas. That is why confirmed black holes are still relatively few in number, even though models suggest there should be very many. When astronomers calculate how many stellar mass black holes the Milky Way might contain, they often arrive at numbers around 100 million. It sounds vast, and it is, but it must be placed alongside the fact that our galaxy holds on the order of 200 to 400 billion stars, spread out over such an enormous population and volume. Black holes become rare encounters. You could travel for light years between stars and never come near one. They are numerous as a class, but each individual is secluded in its own pocket of space. To create a stellar mass black hole in the first place, a star must start out quite massive. The current understanding is that a progenitor star generally needs at least about 18 to 20 times the mass of the Sun for its core to collapse into a black hole at the end of its life. When such a star exhausts its nuclear fuel, its core can no longer support the weight of the layers above it. Gravity overwhelms the internal pressure. The core collapses, temperatures and densities soar, and a powerful supernova explosion blasts the outer layers into space. In the heart of that collapsing core, matter is compressed into an extraordinarily dense state. If the mass of the core exceeds a certain limit, not even the degeneracy pressure that resists further compression in white dwarfs and neutron stars can hold back gravity. Nothing can stop the collapse until it is confined within a region from which light itself cannot escape. The boundary of this region is called the Schwarzschild radius, a notional sphere whose size depends only on the mass of the black hole. Cross that boundary, and escape is no longer possible. What was once a star becomes an object whose internal behavior is described by equations that stretch our familiar physics to its limits. One of the closest known black holes to Earth is found in a binary system with the designation a 62000, also known as V616 Monocerotis. It lies about 3,300 light-years away in the direction of the constellation Monoceros, the unicorn. From our vantage point, this system appears as a faint, variable source of light. Hidden within that variability, however, is the signature of an unseen companion. The visible star in this pair is an orange dwarf with a mass roughly half that of the Sunday every 7.75 hours. Less than a third of an Earth day, it completes a full orbit around an invisible partner. The two objects are very close together, locked in a tight embrace. By carefully observing how the visible star moves, how its light shifts slightly in color as it moves toward and away from us, astronomers can estimate the mass of the object it orbits. The answer that falls out of those measurements is around 6.6 times the mass of the Sun for the unseen companion. That is too heavy for a neutron star, which typically has a mass up to about 2 or 3 solar masses. Above that, the known forms of matter inside neutron stars cannot resist collapse. The simplest explanation is that the hidden object in a 62000 is a black hole. The orange dwarf is not left untouched by its massive neighbor. Gravitational forces from the black hole distort its shape, pulling it away from a perfect sphere. It becomes slightly elongated, stretched along the line connecting the two objects. At the point where the gravity of the two bodies balances in a specific way, matter from the outer layers of the dwarf can spill over, flowing toward the black hole. As this gas leaves the surface of the star, it does not dive straight in. The orbital motion of the system gives it sideways momentum, so it curves and spirals, forming an accretion disk around the black hole. In that disk, friction and compression heat the gas to extreme temperatures, causing it to glow in X-rays and visible light. Once again, it is the bright disk, the luminous halo of doomed matter, that betrays the presence of the black hole at its center. There are at least several dozen other stars within the same general region of space as V616 Monocerotis. Many of them likely host their own planetary systems, with worlds circling quietly around their parent stars, unaware of the compact predator in the neighborhood. Over very long timescales, orbits can shift. Perturbations from passing stars, encounters with clouds of gas, or the slow tug of the galaxy's gravitational field may alter trajectories. It is not impossible that, Someday, one of these neighboring stars might wander too close to the black hole. If that were to happen, if a star drifted into the black hole's strong gravitational influence, the outcome would be determined by their relative masses and the details of the encounter. A star that grazes the outer edges of a black hole's reach might be gently deflected or lose only some of its outer layers. A star that ventures closer can be captured, its orbit reshaped into a tight, elongated loop. Each time it comes near, it would lose more material, feeding the black hole and brightening the accretion disk. The interaction between a black hole and its companion depends strongly on their mass ratio and the distance between them. The more massive the black hole and the closer the other object, the stronger the tidal forces, the differential pull of gravity across the object's width. Tidal forces stretch an object along the direction of the gravitational pull and compress it in the perpendicular directions. In gentle cases, they simply distort the shape slightly, like a soft sphere being squeezed. In more extreme cases, tidal forces can do much more. They can draw long streams of matter out of a star, forming channels of gas that lead toward the black hole, feeding and thickening the accretion disk. As the material falls in, it heats and glows, adding to the fiery ring of radiation surrounding the compact object. If the tidal forces become strong enough, if a star or planet passes too close, the object may not survive at all. It can be torn apart, its structure shredded into a stream of gas that wraps itself around the black hole, forming a bright, transient ring of fire where a whole world or star once held itself together. When people think about black holes, they often imagine a dark hole in space that sucks in everything nearby, like an unstoppable vacuum cleaner. That picture is vivid, but it isn't quite right. In terms of gravity, a black hole is not magical. If you took our sun away and replaced it with a black hole of exactly the same mass, the planets would keep following almost the same orbits. They wouldn't suddenly spiral inward. From far enough away, a black hole pulls on space just like any other object with the same mass. Only when you get very close does the difference show itself. Near the event horizon, the boundary where light can no longer escape, the pull becomes so intense that nothing can turn back. But at larger distances, gravity behaves in the same quiet, predictable way. That's why, strangely but reasonably, a black hole can have a stable planetary system with worlds circling around it as if it were a star that has gone dark. There are several ways such a system might form. In one scenario, everything begins after a supernova. A very massive star comes to the end of its life. Its core collapses, and its outer layers explode outward. The core becomes a black hole, while a cloud of hot gas and dust expands around it, glowing, cooling, and gradually thinning. Over long spans of time, patches of that cloud can cool enough to clump under their own gravity. Small knots form first, then larger ones, colliding gently and merging as they sweep up more dust. From those clumps, new objects take shape: planets, moons, swarms of asteroids, and comets. The process is similar to how planets form around young stars, but now the central object is a silent, invisible mass instead of a shining sun. If there is still an accretion disk around the black hole, hot gas falling inward and glowing intensely, its radiation could warm any nearby planets. It might even be strong enough to melt surface ice, creating liquid oceans on worlds that would otherwise be frozen solid. In theory, such a system might offer conditions where complex chemistry, and perhaps life could appear, even though its sun is a halo of hot matter instead of a bright disk in the sky. In a second scenario, the black hole does not start with a fresh cloud, but with a theft. It captures a star that already has its own planetary system. That encounter would be anything but gentle. The gravitational shock would distort orbits, fling some planets away into interstellar space, and drag others into new, tighter paths. Some worlds would be lost, but a few might settle into stable orbits around the black hole, now circling a new kind of central object. Those planets would carry scars of the change. An ice giant that once drifted on the cold outskirts of its old system might be dragged closer to a hot accretion disk. Ice would melt, thick shells would become deep oceans, and the world would change character. A gas giant, similar to Jupiter, if bathed in intense radiation and strong particle winds, might gradually lose its light hydrogen and helium envelope. Over time, that giant could shrink down to its heavy core, a compact, dense Chthonian planet with a rocky or metallic surface, stripped bare by its harsh new environment. The third path involves wanderers. Not every planet stays attached to its birth star forever. Gravitational jostling in young systems, close flybys, and slow perturbations over billions of years can eject planets into deep space. These rogue worlds drift in the dark, no longer tied to any sun, lit only by starlight from far away and any internal heat they still retain. If such a wanderer passes close enough to a black hole, the black hole's gravity can capture it. The planet's path bends from a straight line into a bound orbit, and it becomes a late arriving member of a new, shadowed family. So far, no one has directly observed a full planetary system peacefully orbiting a black hole. Our instruments are still not sensitive enough to find such quiet, distant arrangements with confidence. But nothing in what we know about gravity and planet formation forbids them. They sit well within the possibilities the universe allows, even if we have not yet caught them in the act. Of course, not every orbit is safe. When a planet strays too close to the center of a black hole system, especially if the black hole is very massive, other effects begin to dominate. The hot stream of gas forming the accretion disk can scrape against the planet's outer layers. Over time, that gas can strip away the atmosphere, like a relentless wind tearing at a fragile shell. Friction with the surrounding material can slowly drain the planet's orbital energy, causing it to spiral inward. Meanwhile, the tidal forces grow stronger. Gravity on the side of the planet closer to the black hole is noticeably stronger than on the far side. This difference stretches the planet along the line toward the black hole and squeezes it in the perpendicular directions. If the planet is only moderately close, these tides might merely crack its crust, triggering intense volcanism and seas of magma. But if it gets closer still, the stress can exceed what the planet's structure can bear. At that point, the planet is pulled apart. It is no longer a single world, but a stream of debris. Those fragments wrap around the black hole, forming a glowing arc as they mix with the gas of the accretion disk. Heated to extreme temperatures, they brighten, then gradually blend into the swirling flow. Eventually, all of that matter crosses the event horizon and disappears from our view, adding its mass quietly to the black hole that tore it apart. If you step back from individual systems and look at black holes as a family, astronomers often talk about three main types, grouped by mass. At one end are the giants, the supermassive black holes that live in the centers of galaxies, including our own. In those crowded central regions, Matter is dense, gas collects, stars form in large numbers, especially massive and bright ones. These heavy stars burn through their fuel quickly and end their lives as black holes. Over time, these remnants can migrate toward the galactic center, merging with one another, swallowing nearby stars and gas. With each merger and each meal, they grow. Across hundreds of millions or billions of years, this steady feeding can build black holes with masses of hundreds of millions or even billions of suns. When plenty of gas is still available, these giants are wrapped in enormous accretion disks. The disks glow so fiercely that, in some cases, they outshine all the stars in their host galaxy combined. From great distances, we see these active galactic cores as quasars, brilliant, compact sources that can be visible across the observable universe. Sometimes, even when the galaxy around them is too faint or too distant for us to resolve its shape, the quasar at the center still stands out as a bright, lonely point of light. The second group consists of stellar mass black holes, smaller and quieter but far more common. These form when massive stars reach the ends of their lives, collapse, and explode. The cores left behind, if heavy enough, become black holes with masses of a few suns to a few dozen suns. Most of the time, they are hard to detect. Unless they are actively drawing in matter, forming a glowing accretion disk, producing X-rays, or launching jets, they blend into the darkness. Given enough time and the right circumstances, a stellar mass black hole can grow. It may slowly accrete interstellar gas, nibble at passing material, or merge with other black holes. When two black holes spiral together and combine, they send ripples through space-time itself, gravitational waves that our instruments can now detect. Through a series of such mergers, some of these objects may become what we call intermediate mass black holes, too heavy to be simple stellar remnants, too light to be the giants at galactic centers. They occupy the middle ground in this family portrait. The third class is more speculative: primordial black holes. Their existence has been proposed in some models of the early universe. Right after the Big Bang, the cosmos was filled with hot, dense matter and radiation, not perfectly smooth but rippled with tiny fluctuations, regions slightly denser or thinner than average. In areas where the density was high enough, gravity could have overwhelmed the rapid expansion, and collapse occurred very early, forming black holes when the universe was still young and hot. These primordial black holes, if they exist, would not need to have stellar masses. They could be far smaller, perhaps with masses comparable to mountains or asteroids, compressed into tiny volumes. Theory also suggests that black holes do not last forever, especially the small ones. Through a quantum process known as Hawking radiation, they are expected to slowly lose mass, leaking energy away as particles and radiation. The smaller the black hole, the faster this evaporation proceeds. Near the end of their lives, as their mass shrinks, this evaporation accelerates. The black hole would radiate more and more intensely, ending in a brief, powerful burst of energy, a final flare before disappearing. Calculations show that primordial black holes, with masses around 10 to the power of 12 kilograms, far lighter than any star, but enormously heavy by everyday standards, would be reaching the ends of their lives around the present age of the universe. If such objects were common, we might expect to see occasional sudden bursts of high-energy radiation as they vanish. So far, no clear, unambiguous signals of this kind have been found. If primordial black holes exist, They are either rare or very well hidden. A related idea is that of quantum black holes, tiny black holes that might form in extremely high-energy particle collisions. In some extended theories of physics, if enough energy is concentrated in a very small region, space-time itself might curve strongly enough to create a microscopic black hole. In nature, collisions of ultra-high energy cosmic rays could, in principle, reach those conditions. In laboratories, even our most powerful particle accelerators fall short of such extremes, though they come closer than anything we can otherwise create. Even if a quantum black hole were to form, its life would be unimaginably brief. Estimates suggest it would evaporate almost instantly through Hawking radiation, disappearing before any detector could really watch it in detail. Its existence would be more like a whisper than a shout, a blip of energy that comes and goes too fast to hold. For now, quantum black holes remain mostly in the realm of equations and thought experiments, a possible feature of reality that has not yet stepped into the light of direct observation. While some of the most compact objects in the universe still live mostly on paper, in equations and thought experiments, others have already announced themselves in ways we can't ignore. Not with light, exactly, but with rhythm. Before astronomers understood what they were, they heard them as a kind of cosmic ticking, regular and insistent, like a heartbeat echoing across the dark. In July of 1967, at Cambridge University, a young postgraduate student named Jocelyn Bell was watching the traces from a radio telescope. The instrument swept the sky, turning faint radio waves from space into lines of ink on long rolls of paper. One day, among the usual messy patterns of noise and drifting signals, Jocelyn noticed something odd, a series of pulses that arrived with uncanny regularity. They were not smeared or random. They came like clockwork, from a spot in the sky that was otherwise unknown. The team kept the result quiet at first, checking and rechecking their equipment. The pulses were so regular that they almost felt too tidy to be natural. For a while, half joking and half serious, they labeled the source LGM, one short for Little Green Men 1. The name captured the uneasy thought that maybe, just maybe, they were hearing a beacon from an alien civilization, repeating the same signal over and over to be noticed. Then more sources turned up. Jocelyn and her colleagues found 3 other places in the sky giving off similar pulses. If one strange source might be a message, 4 looked much more like a pattern of nature. Whatever was causing these bursts seemed to be something the universe did on its own, not a deliberate attempt to speak to us. It took years of observation and interpretation for the picture to come into focus. The phenomenon stayed under careful study for about 7 years. Eventually, the work led to a Nobel Prize for Jocelyn Bell's thesis advisor, and the original object acquired a more formal name, PSRB 1919+21. It turned out to be the first recorded example of a new class of celestial object. Its position was tracked to the small constellation Vulpecula, the Little Fox, about 2,283 light-years away. News of PSRB 1919+21 was made public in February of 1968. By the following year, astronomers had detected pulses from dozens more sources. The list grew, and with it came a new word. These objects, with their repeating bursts, were christened pulsars. Around the same time, another important early source of this kind of signal, known as PP 0943, was identified by Soviet astronomers in the constellation Leo. The more of these pulsing beacons appeared, the more they fed the imagination. For a while, one of the most popular ideas in the public mind was that pulsars might be ultra-powerful radio beacons built by distant civilizations, sweeping their beams through space like lighthouses in a dark sea. The lighthouse image stayed, but the explanation shifted. As data accumulated and theories matured, astronomers came to agree that the regular pulses were not artificial. They were coming from neutron stars, stellar remnants so dense that a teaspoon of their material would outweigh a mountain. When a massive star explodes and its core collapses, the remaining ball of neutrons can spin rapidly, carrying the star's angular momentum into a far more compact form. Today, the basic picture is this. A pulsar is a spinning neutron star with a strong magnetic field. Charged particles moving along its magnetic field lines generate beams of radio waves, or, in some cases, X-rays or gamma rays that shoot out from the magnetic poles. If those beams happen to cross our line of sight as the star spins, we see a pulse each time they sweep past. It is like watching the beam of a lighthouse from far away. You only see light when the narrow beam happens to point towards you. By 2008, around 1,790 pulsars had been cataloged. All of them were powerful sources of pulsed radio emission in space, ticking away in the background of the cosmos. The pulsars closest to us lie tens of light years from the sun, still far, but close enough in galactic terms that their signals can reach us loudly and clearly across the void. As observers kept listening, they found that not all pulsars spoke in the same way. In addition to the radio pulsars, astronomers began to notice pulsating sources that flared in X-rays. These were given their own name, X-ray pulsars. Like their radio cousins, X-ray pulsars are thought to be highly magnetized neutron stars. The difference lies in what powers their light. Radio pulsars draw on their own rotation. As they radiate, they slowly lose rotational energy and spin down over time. Their pulses lengthen. Their ticking gradually slows. X-ray pulsars, by contrast, are usually part of close binary systems. They pull in matter from a companion star, often forming an accretion disk. As this material spirals inward, it releases gravitational energy, heating up and emitting intense X-rays. The neutron star is fed, its spin can be spun up, and the energy we see comes not just from rotation, but from the steady rain of infalling gas. An accretion disk forms when material is captured from the companion gas flowing off the companion's surface, or from a shared envelope. Over long periods, as the neutron star feeds, its mass and spin rate build up. X-ray pulsars can rotate astonishingly fast. Where an average radio pulsar might complete one rotation in anything from a few seconds to a fraction of a second, an X-ray pulsar can spin hundreds of times in the same interval. Among these fast spinners are the millisecond pulsars, neutron stars that whirl around their axes every 1 to 10 milliseconds. They are some of the most rapid rotators known in the universe, turning hundreds of times each second. Most of them live in binary systems, and their incredible spin rates are understood as the result of long periods of accretion. The neutron star gets recycled, spun up by the angular momentum of the material it steals from its companion. One particularly intriguing object of this kind was noticed relatively recently, and it lies not impossibly far from us on the galactic scale. Its designation is J123 plus 38. Astronomers first became interested in its source as the 21st century was beginning, but the pulses were only clearly detected at Earth a bit later, around 2017. This object holds a quiet distinction. It was the first millisecond optical pulsar ever discovered, the first time such rapid pulsations were seen directly in visible light. At its heart, J123+38 is also a neutron star, with a rotation period of about 1.69 milliseconds. In other words, it spins almost 600 times per second. This rate is several times higher than that of typical radio pulsars. The neutron star shares its system with a lighter companion, forming a binary. The companion has a mass of roughly 0.2 times that of the Sunday. The two objects orbit each other closely, with the pulsar circling its partner once every 4.45 hours, a tight, fast dance compared to the leisurely year-long orbit of Earth around the Sunday. The system lies about 42,000 light-years away, out toward the more distant regions of our galaxy. J123+38 itself is probably not an especially massive neutron star. Its exact properties remain to be pinned down in detail. For a time, it was treated simply as a radio pulsar, another entry in the growing catalog. But in 2013, observers noticed something odd. Its radio pulses, once regular, began to fade and even disappear at times. At the same time, it showed brightening in X-rays. This behavior suggested that the system was moving between different states. In one phase, the neutron star behaves like a classic radio pulsar. Material from the companion star is still being pulled toward it, but the pressure of the pulsar's own particle wind and radiation keeps that gas from settling into a full accretion disk. The infalling material is thin and cool enough that it doesn't radiate strongly in X-rays. The star's magnetic field and rapid rotation dominate, and we see bright pulses mainly in the radio band, with signals sometimes reaching up into gamma rays. In the second phase, the flow of gas from the companion increases. Now, instead of being blown back, enough material makes it inward to form an accretion disk around the neutron star. The disk heats up as the gas spirals down. X-rays emerge from the hot inner regions, and J123+38 appears as an X-ray source. In this state, the radio pulses weaken or vanish, washed out by the different conditions around the star. J123+38 is one of a small group of so-called transitional pulsars, objects that switch between radio loud and X-ray loud states as the balance between accretion and particle winds shifts. But it adds an extra twist to the story. After its X-ray state was recognized, astronomers detected millisecond pulsations from it in the optical band as well. Earlier observations with the Swift X-ray telescope had shown that, at the time, the neutron star was wrapped in an accretion disk. Now, optical observations revealed that even through the disk, the star's rapid spin could imprint a regular heartbeat onto the visible light we see. One possible explanation is that electrons in the pulsar's magnetosphere, moving at speeds close to that of light, are emitting radiation across a broad range of wavelengths, including optical. The strong magnetic field shapes their paths and energies, and the geometry of the system lets some of that emission escape toward us in a pulsed form. J123+38 is still being watched and studied. Its full personality, the details of its mass, its magnetic field, the exact way it trades energy between rotation and accretion remains only partly revealed. Those who follow it plan to continue listening and looking, catching it in different moods, hoping that each new round of observations will add another small piece to the puzzle of how neutron stars live, feed, and shine in these restless binary relationships. If J123 plus 38 feels like a small, nearby whisper of a neutron star, there are others whose voices come from far, far away, thin and clear across unimaginable distances. Among them is one that, for now, holds a special place in our catalog, the most distant pulsar-like object of its kind that we know of, and one of the brightest. It goes by the name NGC 5907X1, tucked inside a distant galaxy, about 50 million light-years from the Sunday. When its signal was recognized in 2017, it turned out to be astonishingly intense, an ultra-luminous X-ray source shining far brighter than anyone expected a single compact object could. In just one rotation, this pulsar releases as much energy as our sun produces in roughly 3.5 years. All of that power is poured out again and again with each turn. For a long time, astronomers thought that ultra-luminous X-ray sources like this almost had to be black holes. Nothing else seemed massive or efficient enough to throw out so much energy without tearing itself apart. The discovery of NGC 5907X1 changed that picture. It showed that at least some of these extreme sources are not black holes, but neutron stars, pulsars, whose magnetic fields and accretion flows are somehow managing to channel energy with extraordinary effectiveness. Its spin rate adds another layer of strangeness. In 2003, observations indicated that NGC 5907X1 rotated once every 1.43 seconds. By 2014, that period had shortened to about 1.13 seconds. A difference of a few tenths of a second might not sound like much, but for a whole star to change its spin that quickly is dramatic. If Earth could alter its rotation rate in a similar proportion, our day would shrink from 24 hours to around 19. Morning and evening would slide past noticeably faster, and the rhythm of life would be thrown off. Current astrophysical models struggle to explain exactly how NGC 5907X1 shines so brightly without breaking the limits we expect from ordinary physics. Some scientists suspect that a complex, multipolar magnetic field, one with a structure more intricate than a simple north and south pole, may be shaping the flow of matter and radiation in a way that allows more energy to escape. Others propose variations in how the accreting gas is funneled onto the star's surface. For now, the object stands as a quiet challenge, an invitation for deeper and more delicate theories. Not all extreme radiation from the cosmos arrives in the steady, regular heartbeat of a pulsar. Sometimes, space sends us sudden shouts, brief, powerful flashes that wash through our detectors and then vanish, leaving only questions in their wake. Over the last half-century, humankind has been brushed by a few such outbursts. At first, they were not even aimed at the stars. In 1979, a series of U.S. satellites originally designed to monitor nuclear tests on Earth recorded an unusual spike in gamma rays. The signal had all the hallmarks of something happening far above our atmosphere, not within it. It was a single, intense flare, unlike the background noise those instruments usually saw. In 1992, after collecting and comparing more data, astrophysicists began to suspect that there was some unknown kind of object out there with a remarkably high output of electromagnetic radiation. something not yet mapped into the familiar categories of stars, pulsars, or black holes. The sky seemed to be flashing in ways our existing stories couldn't fully explain. In 1998, another gamma-ray flare appeared, this time from the direction of the constellation Aquila, the Eagle. Measuring devices both in space and on the ground registered an anomaly, an outburst coming from tens of thousands of light-years away. It was not as long-lived as a supernova, not as steady as a quasar, but something sharper and more sudden. Then, in 2004, the sky gave perhaps the clearest clue yet. In late December, telescopes around the world were briefly overwhelmed by a blinding flare of gamma rays. For a fraction of a second, detectors saturated. Less than a second after the pulse, every cubic centimeter of space in our solar system was filled with an extra wave of high-energy photons from far beyond. It was the most powerful burst of its kind ever recorded in the history of such observations, and it came from deep within our own galaxy. At first, these events were just data points, spikes on a graph, briefly appearing and then sliding back into silence. Today, we are closer than ever to understanding what lies behind them. The key appears to be another kind of neutron star, even more extreme than a typical pulsar, the magnetar. A magnetar is a neutron star wrapped in an extraordinarily strong magnetic field. Its field strength can reach around 10 to the power of 13 teslas, trillions of times stronger than the magnetic field at Earth's surface. It is one of the rarest and most dangerous kinds of object we know, at least in terms of the radiation it can unleash. Not every massive star that dies becomes a magnetar. When a supermassive star reaches the end of its life, it goes supernova, and several different outcomes are possible. It might leave behind an ordinary neutron star. It might collapse into a black hole. Only one narrow pathway through those possibilities seems to produce a magnetar. In a way, it's like a cosmic version of Russian roulette. Many chambers, one special configuration. The chances are small, but when they line up just so, the result is extraordinary. Scientists are still debating the exact details of this path. One leading idea is that a magnetar is born when a newly formed neutron star begins life spinning very rapidly. In the first few seconds after the core collapse, the combination of its immense internal energy and its rapid rotation can drive a kind of cosmic dynamo. In this scenario, the motion of charged particles inside the young neutron star amplifies its magnetic field to enormous strengths, winding and boosting it in a brief but intense burst of activity. Another possibility brings in a companion star. In some cases, a neutron star can gain energy and angular momentum by accreting material from a partner in a binary system. Matter flows from one star to the neutron star, adding both mass and spin. If the conditions are just right, this extra supply of energy might help build or sustain an exceptionally strong magnetic field, tipping the neutron star into magnetar territory. Astronomers have even discovered a magnetar that appears to be moving fast enough to escape our galaxy, shooting away as if it had received a powerful kick, possibly from the asymmetric blast of the supernova that created it, or from interactions in a disrupted binary. Regardless of which path it follows, once a magnetar exists, it is a study in extremes. It spins on its axis at high speed, with rotation rates that can range from fractions of a second to many times per second, depending on its history. At the same time, Its size is tiny on normal stellar scales. A typical magnetar might be only 20 to 30 kilometers across. Imagine an object the width of a small city, but with a mass greater than that of the Sunday. For comparison, the Moon's diameter is about 3,474 kilometers, roughly 173 times larger than that of an average magnetar. Yet the magnetar outweighs the Moon by an almost incomprehensible factor because its matter is so densely packed. Inside, atoms have been crushed, nuclei are pressed together. The density is so high that a teaspoon of magnetar material would weigh billions of tons. If you could somehow stand on its surface, which you couldn't, you would be torn apart instantly. The gravity would be so intense that your body would be ripped to shreds in a fraction of a second. One example is the magnetar known as 1E 1048.15937, an anomalous X-ray pulsar about 9,000 light-years away in the constellation Carina. The star that gave birth to it likely had a mass 30 to 40 times that of the Sunday. When that star collapsed, its core became this compact, hypermagnetized remnant. The matter inside is compressed to such a degree that even a small object like the metal clip of a fountain pen would weigh billions of tons if it were made out of the magnetar's material. Because of their extreme magnetic fields, magnetars can behave in violent, dramatic ways. Several years ago, NASA astronomers observed a particularly striking event with the Fermi Gamma Ray Space Telescope. They detected intense bursts of X-rays and gamma rays from a magnetar called SGRJ 1,555,418. The pattern suggested that the crust of the star, its rigid outer layer, was cracking under magnetic stress, releasing huge amounts of energy in sudden fractures. The term starquake is sometimes used for these events, a distant cousin to earthquakes, but incomparably more powerful. In those moments, the magnetar's surface shifts and adjusts to the pressure of the magnetic field, wrapping through it. The breaks allow energy to surge out along magnetic field lines, generating pulsed electrical currents and high-energy flares. To us, they arrive as brief, bright flashes across the X-ray and gamma-ray sky, like lightning strokes in a storm we can only see in higher energy light. If an active magnetar of this kind were somehow placed inside our solar system, the consequences would be severe. At its most energetic, a nearby magnetar could strip away Earth's ozone layer in fractions of a second, flooding the surface with harmful radiation. Organic molecules would be shattered. Life, as we know it, would face a sudden and potentially fatal burst of energy. Fortunately, the magnetar closest to us lies at a safe distance, far enough that its tantrums are reduced to gentle flickers by the time they reach our instruments. From pulsars ticking like clocks, to ultra-bright X-ray sources that push our theories, to magnetars cracking their own crusts under invisible pressure, neutron stars show us how strange and varied the universe can be when matter is pressed to its limits. Each one is a compact story of a once-living star, now condensed into a small, dense remnant that still finds ways to speak into the dark through pulses, flares, and the silent pull of gravity that reaches out across space, touching everything that drifts too close. Even at a distance, a magnetar asks for respect. It isn't only the crushing gravity near its surface, or the explosive flares that erupt during a starquake that make it dangerous to approach. Even when it seems calm, its magnetic field stretches far into space, bending and twisting anything that carries electric currents. In theory, a magnetar in a quiet phase could still interfere with electronics hundreds of thousands of kilometers away. Come closer, within roughly 1,000 kilometers or so, and any ordinary object, from a spacecraft to a human body, would be torn apart at the atomic level, its structure shredded by tidal forces and intense radiation. To make sense of the different ways these stars reveal themselves, astronomers began to group magnetars into two main observational families, using short labels you'll see in catalogs instead of long names. One group is called SGR, for soft gamma repeater. The other is AXP, for anomalous X-ray pulsar. The names sound technical, but they're really just shorthand for how these objects shine. In the current picture, SGRs and AXPs are not two completely different kinds of stars, but two phases in the life of the same kind of object. A newborn magnetar, still full of internal energy and with a freshly amplified magnetic field, tends to show up as an SGR. For roughly the first 10,000 years of its life, it can be visible in normal light and will occasionally unleash repeating bursts of relatively soft gamma rays, high-energy photons, but not at the very top of the gamma range. Those bursts are like the star's temper flaring as its crust adjusts to the stress of its field. As time passes, the magnetar's magnetic field gradually weakens. The most violent bursts become rarer. Its emission shifts out of the higher energy gamma band and slides into the X-ray range. In this quieter, older phase, the object appears to us as an anomalous X-ray pulsar, an AXP. It is still a magnetar, still a neutron star with an intense field, but its fireworks have dimmed and its light has moved to a slightly gentler part of the spectrum. Across the whole universe, there may be billions of neutron stars, formed from the deaths of massive stars over cosmic time. Among that enormous population, the number of known magnetar candidates is tiny, on the order of only a few dozen. In the Milky Way itself, we've identified roughly a dozen likely magnetars so far. The closest one carries the designation 1E 2259 plus 586. It lies about 4 kiloparsecs away, which is around 13,000 light-years from Earth. It is classified as a soft gamma repeater. If a starquake were to crack its crust and send out a burst, the wave of energy reaching us would be noticeable mainly to our instruments and the upper layers of our atmosphere. It might cause subtle changes in the ionosphere, the charged region high above the surface, but it would not burn our world. Because magnetars are small, far away, and not particularly bright in visible light, you cannot look up at the night sky and see them with a backyard telescope. They are effectively invisible in ordinary stargazing. To find them, astronomers rely on instruments that can scan the sky in X-rays, gamma rays, or sometimes in infrared. In those bands, magnetars stand out more clearly. Their active magnetic fields, their bursts, and their persistent high-energy emission make them easier to detect, even across thousands of light-years. A dramatic example of this came in 2013, when astronomers announced the discovery of a magnetar surprisingly close to the supermassive black hole at the center of our galaxy. Using several orbiting observatories, including the Chandra X-ray Observatory, they detected SGR 1745-29, a magnetar located only about 3 light-years from the edge of the central black hole's influence. In galactic terms, that is practically next door. To this day, it remains the only neutron star we've found so near to such a massive black hole. Since its discovery, SGR 1745-29 has been watched carefully. Over time, observers noticed that its X-ray brightness seemed lower than might be expected for a magnetar of its type. This raised an appealing question. Could the nearby supermassive black hole somehow be affecting the magnetar, dimming it, or altering its behavior through gravity or magnetic interactions? After a few years of monitoring and modeling, astrophysicists concluded that the distance between the two objects, about 3 light-years, is probably too great for the black hole to play a strong, direct role in the magnetar's current behavior. The gravitational and magnetic fields from the black hole at that distance are not intense enough to reshape the magnetar's internal processes. The more likely explanation is simpler and more intimate. The magnetar itself is changing as it ages. Its magnetic field is relaxing, its energy reserves are being spent, and its emission is slowly fading on its own. That fits with the broader understanding of magnetar lifetimes. Compared to many other stars, magnetars live fast and briefly. Their active life as strongly magnetized objects is thought to last on the order of 1 million years, a short span on cosmic timescales. Over that period, their fields weaken, their bursts become less frequent, and their personalities shift. Some scientists think these gradual changes are what move a magnetar from the SGR category into the AXP category. Fewer gamma-ray flares, more steady X-ray pulses, a quieter demeanor overall. In their later years, after the magnetic field has decayed significantly and the flares have largely stopped, former magnetars may blend into another small family of neutron stars, the so-called thermally emitting isolated neutron stars. These are objects that no longer show strong bursts or dramatic magnetized behavior. Instead, they glow gently in X-rays, their light coming mainly from residual heat leaking out of their interiors. They are like coals cooling after a fire. So far, only about 7 such stars are well known, and together they are affectionately nicknamed the Magnificent Seven. Each one is quiet now, a faint X-ray ember against the sky, yet it's possible that in their youth, some or all of them were once fierce magnetars among the most dangerous deep space objects in our part of the galaxy, proving that will require more time, better instruments, and patient people willing to devote decades to tracing faint clues in distant light. It is the kind of work that stretches across careers, carried by a quiet curiosity about how stars live and change. All of these stories of pulsars, magnetars, and the black holes that sometimes sit nearby are threads in a larger tapestry astronomers call stellar evolution. That phrase simply refers to the long sequence of changes a star goes through during its life. The path it follows depends largely on one key property: its initial mass. A star born heavy will blaze fiercely and live quickly, passing through dramatic phases and ending, perhaps, as a black hole or a neutron star. A star born light will shine more gently, living for billions of years and ending its days in a softer way. The journey of a star begins in a place that is neither bright nor hot. It starts inside a cold, low-pressure cloud of interstellar gas and dust, drifting quietly in the galaxy. For a long time, such a cloud may be stable. Then, perhaps nudged by a passing shock wave or the gravity of neighboring regions, some parts of it become slightly denser than others. Gravity seizes on these tiny differences. Dense patches pull in more material, becoming denser still. As the gas falls inward, the whole region begins to contract. During this collapse, the cloud's irregular shape slowly tightens towards something more spherical. The gravitational potential energy released by matter falling inward is converted into heat and radiation. The interior warms. What begins as a cold, dark clump of gas becomes a glowing protostar, still shrouded in dust but brightening from within. Its temperature rises steadily as the collapse continues. The length of this early, contracting phase depends strongly on the mass of the forming star. For the heaviest stars, gravity pulls so strongly, and the accumulation of gas happens so quickly that this phase can last only about 100,000 years. The protostar heats, contracts, and ignites nuclear fusion in a brief, intense rush. For the lightest stars, those on the edge of being too small to sustain fusion at all, this process can stretch out for billions of years as they slowly gather mass and creep toward the conditions needed for long-term burning. Our sun sits in between these extremes. Its mass is relatively modest, not large enough to live fast, not so small as to linger forever in a half-formed state. Models suggest that the sun spent roughly 110 million years in this first phase, contracting and warming before nuclear fusion in its core stabilized, and it settled into the long, steady middle chapter of its life. That long, quiet stability is what allowed planets to form and life to take root around it. From the birth clouds of cold gas to the final embers of neutron stars and black holes, every stage of stellar evolution is marked by change, slow in some places, violent in others. The strange objects we've been visiting, the Mira-type giants shedding their envelopes, the packed clusters of Westerland 1, the microquasars, the pulsars, the magnetars, are all snapshots along those paths. They are the universe caught in mid-sentence, showing us that even the most solid points of light in the night sky are, in the deepest sense, still in motion, still becoming. Once a young star has been squeezed and warmed enough, there comes a quiet turning point at its center. Deep in the core, the temperature climbs so high and the pressure grows so strong that hydrogen nuclei begin to fuse into helium. At that moment, something remarkable happens. The inward pull of gravity is finally balanced by the outward push of energy from fusion. The long collapse slows, then stops. The newborn star settles. From the outside, nothing dramatic is visible. There is no sudden flash, no sharp border where before ends and after begins. But inside, the struggle is over for now. The star has found a sort of truce. The energy flowing outward from its core counters the weight of the layers above, and the star enters the long, steady stretch astronomers call the main sequence. This is the true beginning of its life as a star, in the familiar sense, the phase that will occupy about 90% of its total lifetime. Our own sun is in this stage now, and will remain here for roughly 11.5 billion years in total. It has already spent almost half that time burning hydrogen quietly in its core. To us, it seems unchanging from year to year, century to century. But like a slow breath, its properties are drifting. When a star first settles on the main sequence, its composition is still very similar to the cloud of interstellar gas it came from, mostly hydrogen. with a smaller amount of helium and traces of heavier elements. For a typical star, about 91% of its atoms are hydrogen. As fusion proceeds in the core, hydrogen is steadily transformed into helium. The helium, being heavier, accumulates. The core slowly contracts and grows denser, which in turn raises its temperature and pressure even more. Higher temperature means faster fusion, and faster fusion means more energy. Over millions and billions of years, this chain of changes gently alters the star's brightness. Our sun, for instance, was dimmer when it first joined the main sequence. Its luminosity back then was only about 70% of what it is today. As fusion has gone on, the core has tightened, the reactions have sped up, and the sun has grown slowly brighter. By the end of its main sequence life, its luminosity will be roughly 2.2 times what we see now. The change is so slow that no single generation notices, but over geologic time, it reshapes climates, oceans, and the fates of worlds. Not every ball of gas that begins to collapse gets to enjoy this long, stable phase. There are borderline cases, objects called subdwarfs, that resemble main sequence stars but miss some of their fullness. Subdwarfs often have fewer heavy elements than ordinary stars and tend to be less luminous for their mass. They show that the path to the main sequence can be complicated. Still, for the vast majority of stars that do reach it, the overall story is similar: a long period of peaceful burning, followed by a departure into something more dramatic. How that final act unfolds depends mostly on mass. A star born with enough fuel and weight can end its life in a spectacular collapse and explosion, a supernova. A lighter star, like our sun, never quite builds up the conditions needed for such violence. It chooses a quieter road. A supernova is one of the brightest events the universe offers. Over a short span, a star's luminosity can surge to billions of times its normal level. Immense amounts of energy are released as the outer layers are blown away. After the peak, the light fades gradually, leaving behind an expanding shell of gas and, in the core, something small and dense, a neutron star or a black hole. That outgoing shell is rich in the products of nuclear burning. Inside stars, lighter elements like hydrogen and helium are fused into heavier ones: carbon, oxygen, silicon, iron, and beyond. In the shock of a supernova, even heavier nuclei can form. These newly forged elements are thrown back into space, mixed into the interstellar medium, and become part of the raw material for future generations of stars and planets. The gold in a ring, the calcium in bones, the iron in blood, all have passed at least once through the hearts of stars and the fires of explosions. If a star's mass is below about 8 times that of the sun, it usually never reaches the conditions needed to explode this way. Instead, after burning hydrogen and later helium, it expands into a red giant, sheds its outer layers more gently, and leaves behind a different kind of relic, a white dwarf. This is a hot, compact remnant, a stellar core stripped of its envelope. A white dwarf is small, with a size comparable to Earth, but it holds a mass similar to that of the Sunday. If our sun were to become a white dwarf, as it is expected to do, its radius would shrink to about 1/100th of its current value. Its volume would be 1,000,000 times smaller. The gravity at its surface would be so strong that a person standing there, if they could somehow survive, would weigh hundreds of thousands of times more than on Earth. White dwarfs no longer generate energy through fusion. They shine only because they are still hot, cooling embers of former stars. Some of the hottest white dwarfs have surface temperatures as high as 70,000 Kelvin, far hotter than the sun's surface. Yet because they are so small, their total luminosities are modest. They are like bright points rather than blazing disks. Inside, the matter in a white dwarf is in a strange state. The nuclei and electrons are packed so tightly that quantum mechanical effects dominate. The dwarf is supported not by the usual pressure of hot gas, but by the degeneracy pressure of electrons, a subtle consequence of the rules that say no two electrons can occupy the same quantum state. Without a source of new energy, though, even this compact object must slowly cool. The closest known white dwarf to us is Sirius B, the faint companion to Sirius A, the brightest star in our night sky. Sirius B lies 8.6 light-years away, sharing a system with its larger, more luminous partner. Its mass is roughly equal to the Sun's, and it is considered one of the more massive white dwarfs known. Its volume is about 1/millionth that of the Sun, and its diameter is not much different from Earth's. It is thought to have become a white dwarf around 120 million years ago. Before that, during its main sequence phase, it may have had about 5 times the Sun's mass, living fast and bright before shrinking into its current compact form. Estimates suggest that white dwarfs may make up somewhere between 3 and 10% of the total stellar population in our galaxy. More strikingly, calculations show that over 97% of all stars we know today are destined to end their lives this way. They will not explode as supernovae or collapse into black holes. They will simply contract, shed, and settle into small, hot cores, then cool. Over immense stretches of time, these white dwarfs will radiate away their heat. Their color will shift from white to yellow, then to red, then beyond the visible spectrum altogether. Eventually, a white dwarf will become so cool and faint that it emits almost no visible light. At that point, it is called a black dwarf, a star remnant that has cooled to near invisibility. This process takes longer than any of us can truly picture. Cooling from a hot white dwarf down to a temperature where it no longer shines invisible light might require tens or hundreds of billions of years. The universe itself, as far as we can tell, is only about 13.8 billion years old. There simply has not been enough time yet for any white dwarf to complete the journey all the way to true blackness. As a result, black dwarfs, as a class, exist for now mostly in theory. Still, astronomers have found white dwarfs that seem to be heading in that direction. Old, very cool remnants with surface temperatures below 4,000 Kelvin. Objects such as WD0346 plus 246 and SDSS J1000 102 plus 4113 are among the faintest and coldest known white dwarfs, perhaps early hints of what black dwarfs will look like when the universe is much older. Models suggest that white dwarfs formed from the first generation of stars might, by now, have cooled to around 3,200 Kelvin dim, reddish sources that blend into the background. Because they are small, dark, and long-lived, black dwarfs have been suggested as possible contributors to the hidden mass in the universe, the mass we infer from gravity but cannot see directly. Whether they truly play a large role in that puzzle is still an open question. To cool a white dwarf all the way down to a temperature as low as 5 Kelvin just a few degrees above absolute zero. Calculations indicate that it might take on the order of a quadrillion years, 1,000 trillion years. That is far beyond the current age of the cosmos. Some theories suggest that another ingredient could affect this long cooling process: dark matter. If dark matter particles can annihilate with one another inside or near a black dwarf, they might produce ordinary photons and inject a trickle of energy. That extra energy could keep a black dwarf glowing faintly for much longer than it otherwise would, delaying its final fade. As long as the galaxy's dark matter halo persists, this slow-burning contribution could continue, keeping the dwarf just a little warmer and more luminous. Eventually, though, even that extra fuel would run out. Over timescales of a sextillion years and beyond, a 1 followed by 21 zeros, the structure of galaxies themselves will change. Dark matter halos may disperse or evolve, reducing the annihilation rates. Once that happens, the last black dwarfs would finally cool completely, settling to the background temperature of whatever the universe has become by then. From our vantage point in this early, bright era, it is likely that we will never see a fully formed black dwarf. Their main lifespan lies in a chapter of cosmic history that will come long after our own. Astronomers sometimes call the age we live in the stellar era, the time when stars are still actively forming, shining, and dying in visible ways. This phase will continue until galaxies exhaust their reserves of interstellar gas, until star formation dwindles and stops. After that, the universe will gradually shift into a different mood. Low-mass stars like our Sun, which can burn for tens or hundreds of billions of years, will finally fade. New stars will become rare. The sky will fill mainly with degenerate objects: white dwarfs, brown dwarfs, black dwarfs, neutron stars, isolated planets. This long interval is sometimes called the degenerate era, a time of slow disintegration, when the bright, youthful universe gives way to a population of fading embers. Further ahead still lies the black hole era, when much of the remaining matter will have been swallowed by black holes or broken down into elementary and subatomic particles. Over unimaginably long times, even black holes are expected to evaporate through processes like Hawking radiation, shedding their mass as faint emissions. The final act, if our current understanding holds, would be an epoch of deep, enduring darkness. With no stars forming, no bright accretion disks, no active black holes, there would be no major sources of energy. The temperature everywhere would drift toward absolute zero. Space would continue to expand. The last rare interactions would grow rarer still. After perhaps 10 to the power of 100 years or more, the universe might reach a state where nothing much changes anymore. A quiet end, not with a bang, but with a long, slow fading. From where we sit now, under a sky still crowded with stars, that ending feels very far away. Each cosmic object we visited in this journey, Mira, with its long tail, the crowded heart of Westerland 1, the restless microquasars, the spinning pulsars, the cracking magnetars, the quiet white dwarfs cooling in the dark, is unique in its own way. We see only a tiny subset of all that exists. Countless stars burned out long before humans ever looked up. Countless more have not yet taken shape in their birth clouds. The mysteries embedded in that vastness are not something to solve all at once. They are an open invitation. Every new observation, every careful study, fills in one more small detail, and raises new questions. Somewhere in the quiet between pulses and flares, expansion and collapse, the universe keeps unfolding its story, and we are just beginning to learn how to listen.